All right, next we have example 3, where we are asked to determine the area of an ellipse. So we are going to go ahead and take a look at the above remark 1 on calculating area. So it's a really interesting result, and there's some cool things that you can do with this that maybe I'll make another video on at some point. But at this point, let's just take a look at this. So it is possible to calculate area using a line integral. We would do this by relating a double integral to a single integral, a line integral, which is Green's theorem. So remember that earlier on, I actually want to turn that method off. There you go. So remember early on that when you take the double integral of the function 1, so for instance, normally a double integral, we would think of it, generically speaking, you've got a two-dimensional domain D, you've got a function of two variables, let's say f of x, y, and then you integrate with respect to however you want to do it. So you can integrate any function you want, but if our function f of x, y equals 1, then this actually represents numerically the answer that you get gives you the area of that domain D. So what we want to do here is think about a way to relate this. So we know that in Green's theorem, as a reminder, is the double integral over some domain D of del f2 del x minus del f1 del y dA. This equals the line integral around the boundary of D of our vector field f dot dr, if you want to write it in that notation, or equivalently as f1 dx plus f2 dy, where of course f1 and f2 are the first and second components of our vector field, capital F. So we know that area is the double integral of 1 dA. So the integrand has to be 1. Well, the integrand here is this expression. So if this expression equals 1, then whatever vector field has that property, where this quantity of its partials equals 1, then this would technically give us the area of D. And that's exactly what we want here. We want to find a vector field F which satisfies this condition. And there's infinitely many options here. You can invent them. They're very easy to come up with. Just write down something for the one component and then figure out what it has to be for the second component to make it work. It's very easy to come up with them. So here are just 3 really basic ones, pretty much the easiest ones. And you can go ahead and verify that this condition up here does equal 1 for each of these fields. Doesn't matter really which one that you use. Sometimes one might be easier than the other. Of course, you're not going to necessarily know that until you go ahead and do it. That's fine. But yeah. So for this problem, what we're going to do is use one of these fields. It doesn't matter. Let's just pick the first field to keep it simple. So example 3, they task us with finding the area of an ellipse. So to find the area of an ellipse, what we're going to do is, well, first we need to describe the ellipse, right? So we need to parameterize it. So let's go ahead and just draw an ellipse. So something like that, okay? So for this ellipse that I drew, I happen to make it elongated in the x direction. So this is the longer direction. That's the semi-major axis. This is the semi-minor axis. Or actually, this is and this is, but whatever. It's elongated in the x direction. We don't have to do this 2 ways because obviously we could just tilt our page and rotate it, and that would give us a different ellipse, but the area is still the same. So let's just assume that this is our ellipse. And let's go ahead and say that this distance here is a. So this is a x-intercept of a, and this would be negative a. This would be b and negative b. So an ellipse is really just an asymmetrical circle, if you want to think about it like that. It's kind of silly, but it's true. And we know that for a circle, so for a circle of radius r, the parameterization is something like r of t equals r cosine t, r sine t. And this would be for t in the interval 0 to 2 pi. Well, an ellipse being a more general version of a circle, right? A circle is a very specific ellipse. An ellipse is sort of like, just like every square is a rectangle, but not every rectangle is a square. Square is very special. The side lengths are the same. Well, a circle is kind of the same thing. A circle doesn't have sides, so to speak, but this ratio here is the same. So these weights. So the value here, the coefficient on cosine, is the same as the coefficient on sine. If it's an ellipse, the displacement in the x direction and the displacement in the y direction are not the same thing. So for us, our ellipse is actually going to be a cosine of t, b sine of t. That's actually, and since we still have to go all the way around, we're still going to have the same range, 0 to 2 pi. But that's how we can kind of argue and think about this. And this is the correct parameterization for an ellipse. So now that we have that parameterization and a domain for it, we can go ahead and let's use our vector field. So let's define capital F to be this first vector field up here. Doesn't matter which one you pick, but let's go ahead and choose that one just for our purposes. Okay, so now we can say, let's go ahead and say that the interior here is D, and that it's Green's theorem, so let's orient this curve counterclockwise, and there is the boundary of D, is that curve. And that's exactly what R is parameterizing, the boundary of D. So the area of D can be found by computing this line integral using this vector field. So we can plug in. This is the integral from 0 to 2 pi. We want to take our vector field 0, comma x. So we want to replace x with what x is equal to. So x is a cosine t. And then we want to dot it with the derivative r prime of t. So this would be negative a sine t, comma b cosine t dt. So we integrate this. Well, actually, we do our dot product first, which will give us ab cosine squared t dt. Actually, let's go ahead and jump up here. So continuing, we'll have, so I'll say the area of D continuing, this is the integral. I'll pull the AB out. And remember that for integrating cosine squared, we're going to use the half angle identity. So recall that cosine squared t is 1 plus cosine of 2t over 2. So really, I'm going to take the constants a and b and 2, because we're going to replace this cosine squared with this. So I'm going to take my 1/2 and my ab out front. So let's go ahead and say that this is ab over 2 integral 0 to 2 pi 1 plus cosine of 2t dt. So ab over 2, we integrate this and we get t plus 1/2 sine of 2t. And that's between 0 and 2 pi. And hopefully you're getting familiar with these kinds of integrals here. Any whole number multiple of pi, when you plug that into a sine function, it spits out 0. So 0 is a whole number multiple of pi, namely 0 times pi. So this plugged into sign gives 0, and 2 pi times 2 is 4 pi, which is an integer multiple of pi, so sine of that is also 0. So this whole term goes to 0 over these bounds. So 0, I'll just say, I'll strike it out. And then that means what we have here is 2 pi minus 0, plugging in here. So 2 pi. So this will become a 2 pi. 2 pi divided by 2 is pi. So AB pi is the area of D. And you can see that if you go ahead after the fact and say, what if A and B are actually the same? And let's say it's R. So in other words, a circle. If we make these displacements in the x and y direction the same amount, let's say that amount is r, then this becomes r squared times pi, or the way that we all say it, pi r squared, which is the usual and expected area of a circle. So this formula does actually reduce into the area of a circle, provided you plug in the same value for a and b.